welcome the seminar, weekly seminars. Before that, I have some announcement. For non-UK participants, okay, so we encourage you to give a lecture in other universities inside the UK. Okay. So the Newton Institute can cover your travel expenses. So hopefully your host will cover your local accommodation, but we encourage you to give a lecture around the UK, university in the UK. The second, we have preprints. Okay, Newton Institute preprints. So if you finish your paper article, you encourage you submit, article, preprints. Also, we have the forum called the other website. There's, you can post the open problem there. Some discussion, online discussions. Even after you leave, if you solve the problem, you started on during your stay here, you can put it there, for discussion. Okay, so the first speaker today, Professor Lagliscu from Romania. He will talk about nonlinear eigenvalue problems for non-homogeneous differential operator.
Thank you very much for the invitation to give a talk at the Newton Institute. My talk is at the interplay between pure and applied nonlinear analysis. I will give several abstract results, but also some applications, especially to non-Newtonian fluids. I would like to dedicate my talk to the memory of my father, who would have been, after tomorrow, 100 years old. Yes. Okay, it's a pleasure to mention at the beginning the list of my collaborators, starting with Patrizia Pucci, who is not only a collaborator, but also a very good friend. We have written several papers together, but also I have learned a lot of things, nice things in mathematics from Patrizia Pucci, who is a master of the maximum principle with James Serrin. As you know, she wrote very important papers in this field. Okay, so a little bit, something about the motivation of my talk. I will start with something related to sublinear eigenvalue problems. And next, in the second part, I will give you several results concerning the Laplace type operators with variable exponent. So you see here, I have divided into two parts my talk. In the first part, it's very easy for me to explain you what happens. In my talk, I will assume that omega in Rn is a bounded domain with smooth boundary. So, as I said I will consider two types of problems. Say problem 1 and problem 2. Very related, in fact. The first one starts from the very classical eigenvalue problem for the Laplace operator. And the second one starts from, say, the Lane-Emden problem. This is something like minus Laplacian u equals to u to p minus 1 u in omega, u equals to 0 on the boundary of omega, where, say, p is bigger than 1 and less than the critical Sobolev exponent. We know here that in the first case, we have a family of eigenvalues, unbounded family of eigenvalues. And here, if you wish, if we put here lambda positive, we have a solution. There is a solution for all lambda positive. This comes from the mountain pass theorem of Ambrosetti and Rabinovitz. In what concerns the first problem, I will show you that it's possible to obtain a very strange result in the following sense. As soon as we modify the right-hand side, namely, if we consider a problem of the type minus Laplacian mu equals to something like lambda fu in omega with u equals to 0 on the boundary of omega, where f is close enough to the linear function. For instance, if u is less than 0, and just to give you an idea, a log, if u is strictly positive, then here the behavior is completely different. Namely, we can show that lambda here in this problem equals to lambda 1 is still an eigenvalue, and there is a tendency of the concentration of the spectrum at plus infinity, in the sense that there is some lambda star positive such that lambda bigger than lambda star is a solution of our problem, say, of our problem 1. So you see here in the linear case, we have a family, a sequence of eigenvalues, while here in the second case, we have a continuous spectrum at plus infinity. In what concerns the second problem, so the starting point is the Ambrosetti-Rabinovitz theorem, but here, for this one, we will replace the Laplace operator with the so-called px Laplace operator, which is defined as the divergence of the gradient of u to px minus 2 gradient u. You see here p is not a constant, like in the case of the Laplace operator, is not p of x equals to p, like in the p Laplace operator, but is a function depending on x. So this is the simplest case. And in what concerns this problem, I will give you several examples showing that it's possible to have a concentration of the spectrum near the origin or at plus infinity, or in both cases, near the origin and at plus infinity. So this is, you see, the main idea of this talk. And now I will explain you what happens with the, okay, I don't know what I have. Yes? It's, okay, very good. Thank you. Okay, so I have started with this problem, the classical eigenvalue problem. And there are some contributions in the anisotropic case, you see here, in the case where there is a potential, a variable potential, even a paper, a very well-known paper by Hess, Peter Hess and Kato. In fact, they have shown that there is the same, absolutely the same result, like in the classical case, if A is, the potential A is non-negative, but strictly positive in a subset of positive measure. What happens in the case where A is indefinite, namely changes sign, this is much more difficult to say. There are some contributions in this direction due to Sulkin and Willem. They proved, in fact, that there is also, under very natural assumptions, there is a sequence of eigenvalues of the problem. The case where the Laplace operator was replaced by the p Laplace operator, so the quasi-linear setting was studied by Lindis, by Anand, and there are also contributions in the same direction in the case of Hardy-Sobolev type operators defined here. Okay, also some contributions for nonlinear elliptic operators. But anyway, in all these cases, it's very important the fact that the operator is homogeneous, positively homogeneous, and of course monotone with respect to a convex cone. The Laplace operator of P, Laplace operator, and so on. So as I have said you in the first part, something concerning the perturbation of the classical eigenvalue problem, even in the case of polyharmonic operators, in this case it's possible to translate the result for polyharmonic operators. And then what happens in the case where we replace for the problem 2 the Laplace operator with more general operators, for instance, operators of this type. Okay, now something concerning these type of operators, the px operators. In fact, okay, at the beginning, I wrote here a quotation of Arnold. He divides mathematics, you see, into 3 parts: cryptography, hydrodynamics, and celestial mechanics. We are very happy because our field is included here, partial differential equations in hydrodynamics, so if we wish, rational calculus here in celestial mechanics, and so on. In the very original style of Arnold, he wrote something like this, you see. And he also mentioned the relationship between these fields. This is one of the pleasures of mathematics, as you see here. Maybe. Maybe. Okay, so the starting point is something concerning the px Laplace operator. You see, even at the beginning of the last century, Bingham observed a strange phenomenon, namely that there are some fluids that flow and they stop spontaneously. These are the so-called Bingham fluids. In fact, fluids of this type were used starting with the 17th century by the Flemish, in the Flemish medium, and Rubens, for instance, painted his famous La Kermesse in 24 hours by using, in fact, the Flemish medium, as you see here. So these fluids are the so-called electrorheological or non-Newtonian fluids or smart fluids, and they have been observed in a rigorous manner by Winslow last century. And a basic property of these fluids is that their viscosity depends on the electric field in the fluid. Okay, there are some phenomena, for instance, the Winslow effect that appears here, and they have been described in several papers, a paper published in Science by Halsey, but also a PhD thesis like here, and they have been studied very intensively in the last few years due to their major applications to image processing or robotics and so on. And I will give you an example at the beginning, say in image processing. This is a paper published by Chen, Levin, and Rao in the SIAM Journal of Applied Mathematics. They consider an input corresponding to shades of gray in a planar domain, and we assume that I is made up of the true image which is corrupted by a noise. Assuming that the noise is additive, we can say that the input is a sum between the true image and the random variable of 0 mean. Okay, now the effect of the noise can be eliminated by minimizing the corresponding energy, which is standard, is defined here. You see the squared of the gradient and the squared of this mean. So here we observe that we have a very standard energy functional, and we have the square of the gradient. The problem here is that smoothing this energy functional corresponds to destroying some small details, for instance, edges and so on. That is why another approach is the so-called total variation smoothing, which is approximately the same, but here we have 1 as power of the gradient. So you see there is a difference, squared and 1. Otherwise, the second term is absolutely the same. There is also a problem here in the sense that this method preserves edges, but also creates other edges with respect to the original image. This is a so-called staircase effect. Taking into account the combination between these two energies, Chen, Levin, and Rao proposed to replace the power of the gradient by a function depending on x, the so-called variable exponent, and p of x, of course, should be, in their case, between 1 and 2. 1 corresponds near 1, p is close to 1, where there are likely to be edges, and close to 2 in the case where there are not edges. And at the same time, the location, the approximate location of the edges can be determined by where the gradient is large. So edges correspond to the case where the gradient is large. The second example is not in image processing, but in electrorheological fluids. So the constitutive law of these fluids is this system where u corresponds to the velocity of the fluid, pi is the pressure, f corresponds to external forces, and s, which appears here, is a stress tensor which has this form, where d is the symmetric part of the gradient. Now, if we replace s in the equation, and if we are looking at the highest order differential term in the equation, we obtain an operator of this type. You see, very close to the px Laplace operator. Anyway, the degenerate case that corresponds to 0 here instead of 1 is exactly the px Laplace operator. So you see, there is a very strong motivation in the study of electrorheological fluids. Now, the second problem, as I have said we consider minus Laplacian u, which was defined here at the beginning, equals to lambda f of u, where f is a smooth function. For instance, t, if t is negative, and h on the positive semi-axis. Let us assume that h has a sublinear growth, as we will describe in what follows. I also point out that it is not necessary to have here t on the negative semi-axis. I have put t just in order to recover the first eigenvalue. Otherwise, it is enough to put a general function on the whole real axis, and we obtain almost the same result. So we assume that h is a smooth function, say character, continuous function, something like this, which has a linear behavior with c less than 1. And this is a natural assumption, technical assumption. At some point, at least one point, the antiderivative is positive, but the behavior of h at plus infinity is sublinear, uniformly with respect to x, as described by this assumption. Now some examples. For instance, sinus of t over 2 satisfies these assumptions, or a logarithm, as I have showed you at the beginning, or even more complicated, g is a weight here, a potential, a positive potential, you see, as described here, and the combination of variable exponents. in some sense, convex-concave combination, convex-concave nonlinear term. So it's possible to put in the right-hand side general nonlinear terms. So we define the first eigenvalue of the Laplace operator. This is standard. And our result is the following. Assume that we have these assumptions fulfilled, then lambda 1, which is here, is also an eigenvalue for our new eigenvalue problem. And the corresponding set of eigenvectors is a cone. Moreover, lambda 1 is isolated. Any lambda less than lambda 1 is not an eigenvalue. So this one is the smallest eigenvalue. But there is some lambda mu1 small enough, bigger than lambda 1, such that starting with these values, all values lambda are also eigenvalues of our problem. So you see here we have a coincidence in the sense that the first eigenvalue of the Laplace operator is also an eigenvalue of our new problem. This comes from the fact that we have assumed that f of t equals to t if t is negative. Otherwise, we obtain another value, but in any case, the result remains true.
So you assume your first eigenfunction is negative.
The first?
The first eigenfunction is negative.
Yes, it doesn't change that. Yes, that is why. The reasoning is very simple, but otherwise we can argue by obtaining another thing. Yes.
I meant, could you change the FU, the case U, positive and negativity, just by switching the...
Maybe, yes, maybe, of course. This is not a problem.
Yeah.
So, and also, as I said, it's possible to put everywhere the same function and so on. So just a little bit about the proof. First of all, any lambda less than lambda 1 is not an eigenvalue of our problem. Then we show, in comparison with the standard eigenvalue problem, that the same lambda 1 is an eigenvalue for our new problem. Then lambda 1 is isolated, as I have said you. Then we are looking at the associated energy functional. We prove that this one is bounded from below and coercive. There are standard arguments from now on. Next, there is some lambda star positive such that for any lambda bigger than lambda star, the infimum of the corresponding energy is negative. And next, this shows that if lambda is big enough, then the energy has a negative global minimum, so we obtain the result and so on. This result can be extended to other classes of operators. I will give you just some ideas about this fact. For the case of polyharmonic operators, next, namely, we consider the ball, the unit ball, say in Rn, and we take absolutely the same problem, just replacing the Laplace operator with the polyharmonic operator with Dirichlet boundary conditions. Okay, here there is a classical result. Due to Patrizia Pucci and James Serrin, they proved that this problem has a family of eigenvalues, absolutely the same properties like in the case of the Laplace operator. They proved that the lowest eigenvalue is simple, okay, and the eigenfunctions are corresponding eigenfunctions are radial, strictly monotone with respect to the distance to the origin, and do not change sign. Absolutely the same result. So it's not difficult to extend the result. We consider absolutely the same problem. F in the right-hand side has the same properties. I don't give you more details, so H is smooth enough. The same properties, absolutely the same as before, and the result is also the same. This shows, in fact, that we have not a discrete spectrum like in the linear case, but a continuous spectrum which concentrates in a neighborhood of plus infinity. Okay, so this is the first problem. Now something about the second problem. You see the second problem, the starting point was this one, the Lane-Emden problem. A problem of this type was studied for the first time by Ambrosetti and Rabinovitz in their paper published in the Journal of Functional Analysis, where they proved this is the first application of the mountain pass theorem. But in our case, you will see that we don't have a mountain pass geometry. You see, in the case where P here is bigger than 1, there is a mountain pass geometry. If P is between 0 and 1, we don't have mountain pass geometry, but the corresponding energy functional is coercive and so on, so there are other arguments, or we have a unique solution, in fact, if you wish, by using the Bresis-Oswald theorem and so on. So there are several arguments in this direction. Here, I will show you that the situation is completely different. So there are new results. And to tell you something about the philosophy of the proof, this is the following one. In the standard case, the minimum and the maximum of P or Q, for instance, are the same because P is a constant function. If P is not a constant function, we have the minimum of P and the maximum of P. So there is a gap between them. And due to this gap, it's possible to obtain striking results, new results, in fact. Okay, so we have the definition. The case where P equals to Q is not interesting because we repeat the same arguments like in the standard case. So we will assume, in fact, that P is different with respect to Q. Something about the functional setting. Now, just a little bit about this one. So we assume that P is a function, a smooth function, say continuous up to the boundary. We denote by C plus the set of all functions of this type. And we consider the two important values, the maximum and the minimum of H. Next, we introduce the corresponding Lebesgue space, which is this one. But you see here, it's not possible to use the same norm because it's not possible to take this quantity to the power 1 over P of x. This depends on x. That is why the corresponding norm is a Luxembourg norm, introduced here, the equivalent, if you wish, of the Lebesgue norm. But this one is difficult to manipulate. In computation, it's difficult to manipulate. And what is the same? It's the same, the dual space of LPX is absolutely the same. The version of the Hölder inequality is this one. So almost the same. An important quantity here is a so-called modular of LPX. This is this quantity, and something about the relationship between the modular and the Luxembourg norm. You see here that the modular is controlled by the Luxembourg norm at some powers. In a more general way, we have a relation of this type. So the modular of U is between this minimum and this maximum of the same quantities. And we have convergence with respect to the Luxembourg norm if and only if we have convergence with respect to the modular. This is also very nice. Now, something which is different with respect to the standard Lebesgue spaces. For instance, Lebesgue spaces with variable exponents do not have the mean continuity property, in the sense that if P is continuous but not constant, of course, in a ball, for instance, then there is some U in this space such that U of x plus h is not in the same space if h is small enough. This was proved by Kovacic and Rakosnik. Next, these spaces, Lebesgue spaces with variable exponent, are not invariant with respect to translation. And also, there are some problems with respect to the Young inequality, in the sense that the Young inequality is valid if and only if P is a constant function. Okay, next, we are looking at the corresponding Sobolev spaces with variable exponent. You see, we denote the corresponding norm, this one. But in this case, in this situation, as proved by Zhikov, in relationship with the so-called Lavrentiev phenomenon, the smooth functions are not dense in this space, That is why he used a condition, the so-called logarithmic Hölder continuity condition. This space is denoted like here. So a function is logarithmic Hölder continuous if satisfies a condition of this type. In such a case, this is a sufficient condition to have that the smooth functions are dense in the Sobolev space with variable exponent. That is why it's possible to introduce the space of functions with 0 on the boundary, like the closure of the space of functions with compact support with respect to this norm. Anyway, this is not a necessary condition as proved by Edmunds and Rakosnik. They showed, in fact, the same result by using, in fact, not the logarithmic Hölder continuity property, but a local monotonicity condition on P of the variable exponent. Okay, now it's possible also the same in Poincaré inequality in the, for the functions in this case. And this is valid if P is continuous, as showed here. But anyway, it was proved that the Poincaré inequality still remains valid if P is not continuous, but not too discontinuous, close enough with respect to a continuous function. Almost continuous function. Now, something about the relationship with the other spaces. So the space of Lipschitz function is included in Sobolev spaces with index bigger than the dimension, and this one is included in the space of log Hölder continuous functions. Okay, in the case where omega is not bounded, it's necessary to impose not only this condition, the standard condition, but also a condition to control the behavior at plus infinity, because omega is unbounded. In such a case, we cannot require that P is in the Sobolev case due to the fact that this integral is infinity. That is why in the case of unbounded domains, these three spaces are independent in some sense. In what sense? In such a situation, if omega is unbounded, we introduce a new Sobolev space with the variable exponent, like here, okay? And these hypotheses, as I said, are independent one with respect to the other. So there is no relationship between them as we have proved, we have showed in the case of bounded domains. Okay, now just a little bit concerning a very classical problem. We consider the very standard minimization problem with respect to Dirichlet boundary conditions on the real line. So U0, with respect to all functions vanishing at the origin and with the value, prescribed value A in the point 1. If P here is a constant function, we know that the minimizer of this problem is linear, namely this one. This is standard. Now, let us assume that P is not a constant function. And we take just a very simple example in terms of the characteristic function. You see? And let us assume that U is a minimizer, and we denote the value at the middle by B. What happens here? U restricted to the first subinterval is a solution of our problem with values 0 and B, and also U in the second part, in the second subinterval. This means, in fact, that these functions, as we have observed before are linear. The Dirichlet energy, the corresponding Dirichlet energy is this one, and if we are looking at the minimum of this energy, this is achieved for this value of B. Okay. Now if we introduce this value and so on, a computation shows that the minimizer is convex if A is bigger than 2/3, concave if a is less than this value, and linear if a equals to 2 over 3. So you see that the behavior, as soon as the exponent is variable, not a constant function, the behavior is completely different with respect to the standard framework. Now what happens? We come back to our problem as we have announced it. So we are looking for the qualitative analysis of solutions in such a case. We are again in the subcritical case as described here. And we assume that the minimum of, this is a natural assumption, we have seen that Q is always strictly bigger than 1. But we assume that the minimum of P is between the minimum of Q and the maximum of Q. You see, such a condition cannot be achieved in the case of constant exponents. If Q is a constant function, it's not possible to have something like this. Okay. Now, the result is that there is some lambda star positive but small enough, such that any lambda positive less than lambda star is an eigenvalue of our problem. I would like to show you that there are plenty of open problems in this situation. Okay, so this is a corresponding subcritical case as known in the nonlinear elliptic equations. But however, it is possible in these cases to have a mixture between subcritical and critical, in the sense that Q is always strictly less than P star, excepting one point. So what happens if Q at some point x0 equals to the critical exponent at that point, and in the other points is subcritical the problem? There are no results in this situation, absolutely no result in this case. Okay, and now some remarks about a problem of this type.
We assume continuity P and Q.
Sorry?
In this theorem, we assume continuity.
Continuity, yes. P and Q are small enough. As I have described before, they are in the space P, C plus omega up to the boundary, so continuous and so on. There are also open problems in the case where P and Q have discontinuities. There are not papers in this direction. Okay, now we consider the corresponding energy functional. Okay, just a little bit. We are looking here. So this corresponds to 1 over P. 1 over P. So it's not possible to put 1 over P before, in front of the integral, because this one depends on x. But however, there are two types of energies here. If we take this term 1 over P of x, gradient of u to P of x, and without this one, namely gradient of u to P of x, I will give you some commentary remarks about this fact. So the remarks are the following. The energy functional is not coercive because we have this assumption in the statement. So we don't have the case corresponding to P between 0 and 1 here. Okay, next. We don't have a mountain pass geometry. The mountain pass geometry corresponds to an assumption of this type. In such a case, we have a solution for any lambda strictly positive, like in the case studied by Ambrosetti and Rabinovitz. So we don't have mountain pass, we don't have coercivity of the energy functional. In such a case, we can prove that there is some phi such that the energy tends to minus infinity as t tends to plus infinity. This shows, in fact, that there is a sequence such that j lambda un tends to c, like in the mountain pass theorem, and this one tends to 0. However, in this case, like in the case corresponding to mountain pass, it's not possible to show that this sequence, this mountain pass sequence, Palais-Mail sequence, excuse me, is bounded in the corresponding Sobolev space. So there is another major problem. That is why the proof is constructed in the following way. we show at the beginning that our energy functional satisfies one geometric condition. This one shows that the level of the energy is bigger on some mountains near the origin. You see, J lambda is bigger than A, strictly positive is the norm of U equals to rho. So this is the first geometric assumption in the mountain pass theorem. This follows from this assumption, our assumption. Next, the second assumption, geometric assumption, shows that there is a second village, but far away with respect to the first one, namely over the mountains. But in fact, we have that there is a village, T phi, but not far away, but very close to the first village. So both villages are not separated by the mountains, but they are on the same side of the mountains. So this is bad from the point of view of the mountain pass theorem. Next, we have a behavior of this type. We show the infimum on the boundary of the energy on the boundary of the ball is strictly positive, and we have something like this. This infimum is negative. Next, this is possible. This shows that it's possible to take epsilon positive less than the difference of this infima, and then we apply the Eckland variational principle to our functional, and we prove that there is some U epsilon, like in the Eckland variational principle, and so on, and so on, and so on, and we conclude that the limit, in fact, is the solution of our problem. So this time, the proof is based on the Eckland variational principle, not on the mountain pass, not on the coercivity of an energy function. Now what happens if we take absolutely the same problem, but here we complicate the things. We have two variable potentials. So you see here the assumptions are the following. These variable potentials are like here. We are again in the subcritical case. You see here the corresponding of the Sobolev exponents. And we take this value. This corresponds to the first eigenvalue of the Laplace operator. But you observe here we have again 1 over P1 of x, 1 over P2 of x. So the result is the following one. This time, any lambda starting with lambda 1, this value is an eigenvalue of our problem. So we have a concentration of the spectrum at plus infinity this time, not near the origin. And at the same time, there is some lambda 0 less or equal to lambda 1, such that any lambda positive but less than lambda 0 is not an eigenvalue of the problem. So we are sure that there is no eigenvalue in a neighborhood of the origin. So the situation is completely different with respect to the previous one. Something about the proof, lambda 1 is positive, lambda 1 is an eigenvalue of our problem. Again, any lambda bigger than lambda 1 is an eigenvalue of our problem. And here, you see, now there is something strange. There are other energies, but without here the contribution of P1. So we don't have the term 1 over P1 of x, 1 over P2 of x. So it's possible to construct two different energies. This is not possible in the case of constant coefficients. And we have again the Rayleigh. This is a Rayleigh quotient. In fact, another Rayleigh quotient is not the same, like in the definition of lambda 1 previously. So, and we prove that this lambda 0 is good. Namely, for any lambda less than lambda 0, we don't have a solution of our problem. Again, what happens about the relationship, in what concerns the relationship between lambda 0 and lambda 1, I expect that this depends on the problem and so on. I'm not sure at all that lambda 0 equals to lambda 1. Okay. As I said, you something concerning the two types of functionals, of energies, if you wish. So this is the energy. We are interested in the minimization of energies of this type. And for a constant, if P of x equals to a constant Q, for instance, this corresponds to the classical Dirichlet energy, which is this one. Okay, so there is a duality, if you wish, between an energy, the minimization of the energy, and the corresponding Euler-Lagrange functional, as showed, for instance, by the very classical Lax-Milgram theorem in the linear case. Okay, so we have something like this. So we have the Euler-Lagrange functional and the energy, or this one. Now what happens here? So if we change the exponent, namely we consider a variable exponent, we obtain an energy of this type. Okay. This energy, the corresponding Euler-Lagrange functional, is this one, with with the presence of the variable exponent here. So here we have removed, we have changed the exponent in the energy. Now what happens if we change the exponent in the Euler-Lagrange functional? So we have a functional of this type, but the corresponding energy is this one. That is why we obtain two types of functionals, this one and this one, without 1 over p of x and with this quantity. And it's important to pay attention at these energies because this makes a difference, you see, as we have shown in the previous result. Now something very related, we will consider in fact the same problem, but this time p is not a constant function. P is a vector function depending on the direction. So we have p1, p2, pn, several functions. We construct again the Sobolev space and so on. But in this case, until now, we have considered the minimum and the maximum of the variable exponent. Now we have n variable exponent, n functions. That is why we will take n maxima and n minima. We consider the corresponding vector here, the corresponding vector here. An important quantity is the maximum of the maxima and the maximum of the minima. We play here, you see, the minimum of the minima, and so on. So we have several quantities. An assumption of this type is also very natural. This corresponds to n bigger than p. N bigger than p. If p are constant, then we have n over p bigger than 1. So the dimension is bigger than p. So for high dimensions, this assumption. And we have the corresponding Sobolev exponents, if you wish, here. So very natural quantities in any case. Okay, this is the equivalent of the Kondrashov compact theorem for Sobolev spaces. Okay, this is a basic reference for the study of anisotropic equations. And now what happens in our case? We consider absolutely the same problem. Absolutely, in the right-hand side is the same. But in the left-hand side, the operator is the same, px Laplace operator, but taking into account that we have several functions, different functions, p1, p2, pn. The first result is the following one. With respect to the different hypotheses that may appear, if we have a situation of this type, a subcritical situation, you see, if we have a situation of this type, this corresponds to mountain pass, in fact, for any lambda, we have a solution for our problem. What happens if we change the hypothesis here? A second case is the following one. If we have, this is natural, this is not a problem. If we have a situation of this type, this, you remember here, this is the minimum of minima, the minimum of minima. Then there is a lambda double star, such that any lambda bigger than this value is an eigenvalue of our problem. So again, a concentration of the spectrum at plus infinity. If we change the assumptions here, if we have an assumption of this type, then there we have a spectrum near the origin. And it's possible to put together these assumptions, and we obtain a corollary of this type. So if we have an assumption of this type, so we have a spectrum both in a neighborhood of the origin and also in a neighborhood of plus infinity. Of course, I don't know what happens, another open problem, what happens between these two values. Okay, so I think that this is enough. Thank you very much.
Any questions?
mentioned the eigenvalue of the Laplacian with weight A.
Yes.
But is there any problem to prove that the spectrum is discrete?
So if A is non-negative, if A is non-negative, this is true. This is true. This is, but if A changes sign, it's more complicated.
But if it's bounded, so
Yes, of course. But under very natural, indefinite potential, this is a problem. Under very general assumptions, this is the problem, not necessarily. For instance, in the paper by Surkin and Willem, they have assumed very general hypothesis about A. Okay, in certain Lebesgue spaces and so on. But in the general situation, it's really difficult to say. It is not known. Even for the P Laplace operator, for instance, there are many open problems here.
Have you considered how big those eigenfunctions, set of eigenfunctions, corresponding eigen?
No, I have obtained until now only
Just one
existence results of this type. I don't have an idea about. I have tried to obtain new results because you see, if we try to repeat, for instance, variational arguments, they are exactly the same. But I have tried to obtain new results, and as I said, this comes from the fact that the minimum, the maximum are different, and so the exponent is not constant like in the classical cases.
Thank you.
Thank you very much. Thank you.